Hello, good morning. Good morning. Can you hear me? Can you hear me?
Yes, can you?
Okay, very good morning. I hope you can hear me clearly, yeah? Okay, can you hear me?
Yes, doctor.
Yes, doctor.
Okay, I think we can start now. Hopefully you can hear me clearly. I'm trying to get a good signal here. You can see my slide? You can hear me?
Yes, doctor.
Okay, good. All right, so we had last week our class test. I had questions last week from you whether we will discuss about the class test. Yes, we will. I will arrange a time, okay, but not today. So for today, we are going to continue our next lecture, lecture 5, which will deals with the constraint models for hyperelastic mature response. Okay, So basically, this is an extension to what we have learned in lecture 4, dealing with linear elasticity. So we will focus on the topic remaining on the case of elastic deformation, which means that we do not consider any plastic deformations. The only difference with what we have learned in lecture 4 is that the elasticity is not linear anymore, which means that we don't have proportionality between stress and strain anymore as what we had in lecture 4. So this is basically the main difference between lecture 5 and lecture 4. And then commonly, the nonlinear elastic mature response is also called as hyperelastic mature response. And the class of materials which show this kind of response, the well-known one is rubber or elastomer, elastic polymer. So this is the topic of our lecture for today. So looking at our schedule, we are now in lecture 5. Out of 6 lectures that we are going to discuss, so we are very much on times on the delivery. So I have times today because this is a very important topic, so I will try to go very slowly. Much of the things I will not explain in detail because you will need to read by yourself in additional any relevant reference book. We have limited times. It is only 2 credits of the lecture, but I'm going to try to just take out some important items which will be relevant for our purpose in this lecture 5. And again, I would strongly suggest you to read more on the reference, on the books related to the hyperelastic mature response. Of course, if you have any questions, you may let me know so that we can address, clear your doubt. If I don't know the answer, then I will say I don't know, and I will try to find out the answer and get back to you in the following sessions. All right? So again, do not hesitate. Just interrupt me during the lecture, or you can also write on the chat box if you have something which are not clear for you and require further clarifications. All right? Okay, this lecture 5 will be divided into 3 sections. Okay, so in the first sections, I'm going to recall the things that you have seen in material science and engineering in semester 1 or semester 2. Okay, we'll deal with material science and engineering, specifically with polymeric materials, and then we will put emphasis on a class of polymeric materials which is called as elastomers or rubber. Okay. And then the idea is that for us to remember the basic important notions relevant to the structure and properties of rubber, because this will be important for us before we go to develop a mathematical equation to describe the stress-strain response of the materials. So 2 approaches will be discussed. The first one is the physical approach. Again, physical approach, to remind you, is that we need to look at the microstructure of the materials. And then secondly, phenomenological approach, in which we do not need to look at in detail the structure of materials. So for today, I think I'm going to discuss only section 1 and section 2, and then leave out the 3rd sections for our discussions next week. Okay, let's have a look back on basic review on the structure and properties of rubber. Let me recall basic introductions to polymers. Yeah. You have learned in year 1 that the word polymer comes from Greek words, poly and meros. Poly means many, meros means that the unit, smaller unit or repeat unit. So basically, polymer composed of repeating structural units which are connected by strong covalent bonding. You have learned also the characteristic of covalent bonding. It is large molecule. That is why it is also commonly called as macromolecule. So consists of long chains molecule. Okay? And then polymers are composed mainly of hydrogen and carbon. They have relatively low density because of their microstructure. And then they have also tendency to soften or decompose at relatively modest temperature. Okay, so temperature becomes important things when it comes to designing a components made of polymer. You have to be careful. You have to take into considerations the temperature at which the polymer will operate. And then some example of polymers are polyethylene. So if you look at the plastic bag, before we introduce the biodegradable, degradable plastic bag in the supermarket, commonly it is made of polyethylene. Okay? And then polyvinyl chloride or PVC, so example of PVC widely used for piping systems. So plastic pipe, polycarbonate is stiff and hard polymer, and then it is commonly used for helmet or for your traveling luggage. Yeah. Polycarbonate is used for that. And then another example, which is relevant for us here, is natural rubber. Okay, this is an example of polymeric materials. Okay, now we move to the structure of polymer. So this is how the typical representations of the structure of polymer, especially as an example here is polyethylene, or typically called as PE. Okay? So as you can see here, you know well that it consists of repeat unit, and the repeat unit in this example is the monomer of ethylene. And then through a chemical process called polymerizations, then we can create a long chains molecule of polyethylene. Okay, so this is the typical representations that we learned in the book. So noting that this is a much simplified representations of what we observe in reality. So this is the 3D representations of how the structures of polymers of polyethylene. It is not a simple straight structure, but instead it consists of zigzag pattern. Okay, so you have here the main chain of carbon-carbon, which is typically called as polymer backbone. Okay, and then between the carbon-carbon, there are strong covalent bondings. And then you have learned in material science that covalent bonding is directional in nature, which means that there is specific angle orientations in which the bonding will be oriented. Okay, and then attached to this polymeric backbone, you have the side group of substituent, and in this case, it is hydrogen. Okay, and then this is the repeat unit that we have here, that we represented in a much simpler way in the book, while actually in reality it is 3D structure. And then there is specific distance between the atoms, and this distance corresponds to the equilibrium's atomic distance, something that we learned in lecture 4 when we want to derive the constitutive equations using the physical approach for linear elastic materials in metals. Okay, so the distance, the typical distance between C atoms are about 1.5 angstrom. Okay. All right. So in the next one, I would like just to recall few terms that you will need to remember and understand, because they are very critical in our purpose to develop a constitutive model. Okay. I will take just some few terms which I believe important. Okay. First is molecular configurations. What does it mean? It corresponds to stereochemical arrangements of atoms in polymeric chain. So configuration is fixed during synthesis, during the polymerization process. And then if you want to change the configurations of the polymer, then you need chemical reactions, which means that you need to break the atomic bonding, the chemical bonding in the polymer. For instance, you have here the example, the illustrations of polytetrafluoroethylene, PTFE structure. It is a fixed configurations. If you want to modify this to create another types of polymer, then you need chemical reaction. You need to break atomic bonding. The second example, similarly, is the structure of PVC, polyvinyl chloride, okay, where you have almost similar to polyethylene, except in one side group here, you have chlorine atoms, okay? So again, if you want to modify the configurations, the chemical arrangements, you need chemical reactions, which means that you need to break chemical or atomic bonding. So this is configurations. This is the meaning of configurations in the context of molecular of polymer. Okay. The next one, which is very important for us to understand the mechanical behavior of elastomeric materials or rubber, is molecular conformations, or simply molecular shape. What does it mean? It is actually a geometrical arrangements of atoms in polymer chains due to bond rotations and bending. Let me take an example. For instance, this is the illustration in blue, the illustration of one single chain of polymer, one strand of polymer chain. Okay, so statistical mechanics, more precisely, teach us that the high probability you will find the shape of the single chains in highly coiled structure. So if I take one strand of polymeric chain, this is one end, this is another end. In between, you have long chains molecule with the shape which is highly random, highly coiled. So this shape is called as conformations. So conformation is basically a shape. How a single chain or polymeric chains have a shape. This is conformations. Okay. Of course, in reality, because you have in polymer, you have lots number of polymeric chains, you cannot precisely define the shape of the polymer. Okay. What you can do is represent it in the form of probability functions describing the probability shape of the polymer. Okay, so this molecular conformation is actually actual state of the chain. It is a shape. Because it is simply a shape, you can modify a shape. So you can disturb the shape. How to disturb the shape? Typically, if you have polymer, you deform it, the polymer. If you have tensile sample made of polymeric materials, when you stretch it, actually, from the chain point of view, you change the shape of the molecular conformations. You change the shape, okay? So if you want to change the shape, you don't need to break, you don't need chemical reactions. You don't need to break the covalent bonding in the polymeric backbone, unlike in the case of configurations, molecular configuration, when we need to cut, when we need to break the atomic bonding in the polymeric backbone. Okay, here you don't need it. You just simply change the shape, basically. And this is what happens in polymer, and specifically because we are going to talk about rubber. If you imagine a rubber, you can stretch it by certain amount of strain at large amount of strain. Okay, so what happened is that you really need to disturb the shape of the conformation. Okay, how is the mechanisms of the change of the conformation? It is through a process called as bond rotations and bending. So here, if I have simple illustrations of three adjacent atoms, they are connected through covalent bonding. Okay, again, you need to look back in material science. Covalent bondings are directional in nature. So it made certain angle here, okay, certain specific angle. So what happened is that these atoms can rotate about this axis, okay, making a cone, making a circle here, as long as the angle between two successive atomic bond remains at approximately 109 degrees. Okay, so if I now illustrate previously the polymeric backbone, the straight polymer backbone in the form of zigzag pattern, so each of the atoms can rotate with respect to the atomic bonding in the previous connections here. Okay, these atoms can rotate about this axis. This atom can rotate about this axis, and so on and so forth. So that when you disturb the shape of the polymeric chains, basically the atoms will rotate and bend, and finally having this shape. So again, the deformations of polymer, or if we talk about the deformations more specifically of rubber, from microstructure standpoint, from the molecular standpoint, is that we change the shape of the polymeric chain. And then this is through bond rotations and bond bending. If we want to change the conformations or the shape, we don't need chemical reactions. We don't need to break the atomic bond in the polymeric backbone. Okay. I hope this is clear. Is there any question so far? Okay, hopefully it is clear for all of you. Now, let's have a look at classifications of solid polymers. Polymers can be in the form of liquid or polymeric melt. We are focusing here as mechanical engineer on the solid polymers, which means that polymers which have a solid in a solid state. Okay. Can you hear me? Is it still clear, the connections?
Yes, doctor.
All right, good. I will continue. Okay, hold on. Maybe I need to check. Okay, so there are three large classifications of polymer. So first is plastics, elastomers, and then fiber. So let's have a look one by one, the difference between these types of polymer. Okay. First is plastics. Plastic basically have some structural rigidity under mechanical load. So they are relatively have certain stiffness, significant stiffness as compared to elastomer, for instance. Okay. And then you can have plastics with wide variety of properties. You can have plastic which is relatively ductile, which means that you can stretch them at large strain before they undergo fracture, for instance, polyethylene. Or you can have also relatively stiff polymer, for instance, which means that you cannot draw them at large amount of strain before fracture, polycarbonate, for instance. Yeah? So you can have a wide varieties of properties when you deal with plastics. And then looking at the structure of polymeric chain, you can have plastics either in the form of fully amorphous structure, which means that the polymeric chains are at random state. So they are irregular state, coil state. Okay. Or you can have semi-crystalline state. Semi-crystalline means that you can have some polymeric chains which are totally random. And then in some part, you have some regularity of polymeric chains to form the crystal. Because it is partially crystalline, we call it as semi-crystalline. Okay. And then you can also have plastics in the form of thermoplastics or thermosets. This is something that you have learned also. The idea is simply the characteristic of plastic with respect to thermal cyclic loading. Thermoplastic basically means that if you heat it, it will melt. If you solidify, if you cool it, then it will solidify. And then the process can be repeated. If you don't, the typical, the common process, for instance, injection molding, You use mold to manufacture a certain product made of plastic. You heat the plastic, melt it, and after that you cool it, put it in the mold, and then you have the product. If you don't like the product, you can simply repeat, heat again, and then change the mold, modify the mold, and then pour back again to the mold to have a certain specific shape. So you can repeat the process, this thermal process. Thermoset, you cannot do that. Okay? When you heat it, and then you cool it, certain chemical reactions occur. Okay? You form the network. So once you cool it, if you don't like it, you cannot reheat it, because you need high amount of thermal energy. You need to bring it to very high temperature to break the bond. But when you break the bond, basically you break also the polymeric backbone. So you destroy the polymer. So this is the process that it cannot be repeated. That is why it is called as thermoset. Once the process is completed, you cannot undo it, unlike thermoplastic. Elastomer, which will be our focus. They have a specific characteristic of being able to undergo deformations at large strain, but elastically. So you can stretch them elastically to 3 or 4 times their original length, but the deformation remains elastic without plastic deformations. It is called as high reversible deformability. And then this capability is one of the reasons is because they are amorphous. They are at the amorphous state, at least before any applications of mechanical load. So if you look at the microstructure of elastomer, then they are amorphous, highly random, highly coiled structure of polymeric chain. And then there is a characteristic called as glass transition temperature. You have learned about this. So for elastomer, the glass transition temperature is below room temperature. Okay, so what is the glass transition temperature? Basically, to recall, is that this is the temperature which highlight the difference characteristic of polymer between glassy or stiff polymers to become rubbery or soft polymers. Okay, if you bring a polymer to temperature higher than the glass transition temperature, then the polymer will become rubbery. So you have like elastomer. If you bring the polymer to the temperature lower than the glass transition temperature, then it becomes glassy polymer. It becomes stiff like plastic. Okay, so different polymers will have different glass transition temperature. Elastomers have glass transition temperature which is way below room temperature. Because it is way below room temperature, at room temperature they behave like rubber, like elastomer. Okay. And then we have learned this one in the thermodynamic of deformations, that in the case of elastomers or rubber, elastic deformation is entirely due to the change of entropy. We change the irregularity of the microstructure of the materials. Unlike in metals, where the elasticity is attributed to the change of the energy, internal energy, while here is the change of entropy. We are going to have a look back there. We can have also polymers in the form of fibers. You know, fibers is a filament, basically, having at least, well, about 100 to 1 length to diameter ratio. So certain class of polymers are capable to be drawn to form filaments, okay, to form a fiber. And then because they are being drawn, okay, what happened is that the polymeric chains are being oriented on the directions of the drawing. Because all the polymeric chains are oriented along the direction of drawing, they create intermolecular force, they create a crystal. So what happened is that what we see at macroscopic scale is that we obtain materials which possess high tensile strength and high modulus of elasticity. And then in order for a polymer to be able to be drawn into long filaments, there is also molecular requirements. So you need to have linear polymeric chains, which means that you need to have low amount of branch, because branch will make drawing to form a fiber more difficult. So the less the number of branch, the easier for a polymer to be made a fiber. Okay. So again, in this lecture, we are going to focus on elastomers. So what are the requirements for a polymer to become elastomers? So I will look at from molecular requirements. In which situations a polymer can become elastomer? This the questions basically. So first, if a polymer wants to become elastomers, then these are at least the 3 molecular requirements that must be met. First is that it must not easily crystallize, which means that it has to be completely amorphous. Because when you have a crystal, what happens is that you will end up with stiff materials. The more crystal you have, the stiffer the materials. Okay. While we know that elastomer is elastic, capable to be drawn a large strain, and it is relatively a soft material. And then the second requirement is that you need to have highly flexible polymeric chains, so that you have easy chain bond rotation to respond to applied force. So you have to be able to change the shape of the polymeric chains relatively easy. Okay, you have to be able to change the conformations at relatively easy way. Okay, and this is made possible by having the glass transition temperature much lower than the room temperature, because at that temperature, at the temperature higher than the glass transition temperature, you can have easy chains bond rotations. Okay, the chains become more flexible basically. And then the third one is that if we observe elastomer, is that when you pull it 2-3 times their original length and then you release the load, it snaps back to its initial shape. So elastic deformations. How it is possible? So you need to create a network structure so that we avoid irreversible slippage, mean that we avoid plastic deformations to make it easy. Okay. So how we can do that? Technically, there are a number of ways, and one of the example how we create network structure is that through vulcanizations process. So what is vulcanization process? You have learned also here in material science. Okay, so it is a process of cross-linking, which means that you join 2 polymeric chain. Okay, through chemical reactions. So you create a crosslink. Crosslink basically is a chemical bond, atomic bond, by heating elastomer with sulfur compounds. So for instance here, you have a monomer of isoprene. This is the natural rubber. This is another monomer from the polymeric chains, and then you heat it and then plus the sulfur. So what happens is that you create the bonding here, additional bonding, to make sure that one chain is connected to another chain. This is called as cross-linking. So this is another illustration. You have one chain here and another chain there, and then we create vulcanizations, which means that you tied up one part of the chain here to another part of the chain here. So when you pull, for instance, in horizontal directions, and then you remove the load, then this will act as an anchor point to snap back the polymeric chains to initial shape, to its initial conformations. Okay. All right. So I have been using the word elastomers and rubber interchangeably. Okay. It is different terms actually. Elastomer is elastic polymer. So all polymer which are elastic, having meet all the requirements to become elastomer. Not all rubbers are elastomer. Okay. Not all rubber is highly elastic. But in this context, so I will just use the 2 terms for the same meaning. If I use elastomer, it means that it is elastic polymer. When I use rubber, it means that it is also elastic rubber, elastic polymer. Okay. So not to confuse everyone here. Okay, now I have introduced back the microstructure, something that you have learned in year 1. Okay. Now, as mechanical engineers, let's have a look what is the consequence of the structure that we have to the mechanical behavior, to the stress strain characteristic of the materials. So let's imagine that I do the tensile test on rubber sample. One sample is vulcanized, which means that after cross-linking, the other one is unvulcanized. So this is the response that I have for vulcanized. And sorry, the vulcanized is the red one, and unvulcanized is the blue one. So let's focus on vulcanized one because this is our main discussions. So elastic polymer elastomers, which is cross-linked through vulcanization process. Okay, so here what we see is that this is strain, this is stress. Strain of 1 means that it is 100%. So you stretch it 2 times of its original length. The strain of 2 means that 200%, which means that you stretch it 3 times that is initial length, and so on and so forth here until 6, 7 times. You can imagine that this is a class of materials capable to be stretched very large strain. Okay, and then another thing is that it is occurring at elasticity, which means that it does not involve plastic deformations. So it is large elastic strain, which means that if I draw here to 6 and then I remove the load, it will bounce back to its initial shape here. Okay, depending on types of elastomer, some can be drawn elastically up to 2, 3, 4 times. Others can be drawn to higher level of the strain, depend on the types of elastomers. Okay, so the first characteristic that we observe is that they are capable to go large elastic strain. So this is really different with what we have in metals. We see the stress strain curve of metals, and then the elastic response occur at a very narrow regions of the stress strain curve. Only few percents from the stress strain curve, 0.0 something, that you can have elastic deformation. Beyond that, you have plastic deformations. But here, few 100% of strain, you are still having elastic deformations. So the first thing, the material is capable to undergo large elastic strain. The second thing is that if you see, so this is the elastic portions, and then compared to what we have seen from metals, the elastic response for metals occur at the very narrow regions where the stress-strain relationship is linear. You have proportionality. You have certain fixed slope corresponding to elastic modulus. Here, as you can see, the slope is not constant depending on how much you stretch it. Initially, you have certain slope here, certain stiffness. If you stretch it up to strain equal to 2, this is the slope. So it is as if the stiffness of materials evolve depending on how much you stretch it. So it is a non-linear response. So you have non-linear stress-strain response here, as clearly can be seen from the stress-strain curve. And another thing is that many of the elastomeric materials undergo deformation at constant volume. So what happened is that if you measure the volume of rubber specimen before undergoing deformations and after undergoing deformations, they are typically the same. So the deformations occur at constant volume, and this is characteristic called as incompressible materials. Okay. Okay, so now we have seen the brief review on the microstructure. We have seen the basic stress-strain response of rubber. Our objective here is to develop mathematical equation, stress-strain equations to describe stress-strain characteristic of rubber, of elastomer, which are highly nonlinear. Okay, the material is capable to undergo elastic strain, and then also the stress-strain response is non-linear. So as I mentioned earlier, in order for us to develop the mathematical equations, I will use 2 different approaches, physical approach and phenomenological approach. And for today, I'm going to focus only on physical approach and leave phenomenological approach for next week. All right. So just to recall again here, before we start by how we can derive the stress strain equations or constitutive equations or the constitutive model for nonlinear elastic material response, let me show back again here the things that we have seen in the thermodynamic of deformations in lecture 3. Okay, so here is the illustrations of the structures of rubber. It consists of highly coiled and entangled molecules. It is random, amorphous structure. If it is highly random, it means that the entropy is relatively high. After that, imagine that because the sample is stretched along these directions, what will happen to this is that the change will tend to align along directions of stretching. Okay. So the initial structure, which was highly irregular, become more regular now with the deformations. And then from the entropy standpoint, we have initially relatively high entropy. With stretching, we have lower entropy now, okay, because we have a more regular structure where the polymeric chains are oriented along the directions of stretching. And then the stress equations we have seen in the thermodynamic in deformation is simply F over A, 1 over A, and then F is simply differentiations of the Helmholtz free energy with respect to deformation at constant temperature. Okay. And then because we know that the elastic deformation of rubber can be associated entirely to the change of entropy, then we replace here the free energy with respect to this one. We change it to this one. So become T, the change of entropy with respect to deformations. So which means that if we want to write the equation for the stress, we need to identify what is ds, dl, how the entropy will change with deformations. And in this physical approach, we need to look at back to the microstructure and make then the analysis to determine how actually the entropy will change with deformations. Okay. If you have any questions, please let me know. Or you can write it in the chat box, okay, before things get too complex. Again, a lot of things that I will talk in the following slide require the knowledge of statistical mechanics, okay? It is beyond the scope of our lecture here. So what I'm going to do is that just take some result from the statistical mechanics that will be useful for us. And then if you would like to know more about it, so please have a look to the literature, to the reference, to the book related to statistical mechanics as applied to rubber elasticity. Okay. Now, before I proceed, there are a few things here. All this while, when we talk about the thermodynamic of deformations, we talk about free energy, and then we talk about entropy. The free energy, the unit is joule. The entropy, the unit is joule per Kelvin. Okay. So in the treatment of rubber elasticity, actually, it is much more convenient to work in the form of density. If you talk about energy, it is energy density, which means that energy per unit volume of the materials. Or if you talk entropy, it is more convenient to talk entropy density, which means that entropy per unit of materials volume. So in these situations, previously I used notation psi bar for free energy. Now here it becomes psi only, and the unit change becomes joule per meter cube. This is entropy, joule per Kelvin. This is entropy per unit of volume. The unit will be joule per Kelvin per meter cube. Okay, so now we have learned previously here that F is d psi bar per dl. This is F capital. Okay, please pay attention. Here we have small f, lowercase f, which is similarly differentiations of the energy density, the free energy density, with respect to deformations. So I will switch back to the previous slide to highlight the difference. This is psi bar over L, and this is large F, capital F. While here is small f, and this is the free energy density over deformation. So the small f here is the force per unit of volume. So it is Newton per meter cube, because the energy we change to become energy density. And then for elastomer, it is equal to minus T ds dl at constant temperature. Okay, and S here is the entropy density. And this is equal to the large F that we had before over the volume. So that when we calculate the stress, now sigma equal to F point over A, it is equal to small f time volume over A. Volume over cross-section is the length. So it becomes minus the length, well, T ds dlt from these equations. So this is how we are going to develop the stress-strain equations for rubber. In the next stage, we need to determine what is ds dl, how the entropy density change with deformations in rubber materials. Okay, so this is the step how we can derive the materials model, the mathematical equations to describe stress-strain response. I classified it into 6 steps. Okay, some of the steps I will discuss in detail, some I will not. Okay, to make things easy. So this is step 1, step 2, until step 6. Let me go backward by starting from stage 6 here, step 6. Our main goal is to have the equation for stress-strain behavior. So stress equation or materials model. Or more precisely, I want to calculate sigma equal to small f times L based on the previous slide here. Yeah, because F times V over A is L. Okay, so F times L. That is my objective actually. How to do that? Then I know from the thermodynamics that the small f is differentiations of free energy density with deformations. And for rubber materials, which is entropic elasticity, the change of the free energy density with deformation can be given by minus T, the change of entropy density with respect to deformations. And then which I can approximate as minus T, differentiation is ds over dl. The change of entropy density with the change of the length in the materials. Something to highlight here is that delta S here is the change of entropy. Entropy corresponds to the irregularity of the whole materials. And materials consist of a lot of polymeric chains. It is a network structure. Okay, which means that this delta S that I have here is actually the total summations of the change of entropy of each individual polymeric chain, which means that this delta S that I have in step number 5 can be obtained from step number 4 here. Well, delta S is simply the sum of the change of entropy with deformations in the whole network. And then delta SI is individual polymeric chains. You simply sum up. Okay. Which means that now I need to look at single chain. I need to identify how is actually the entropy density change with deformation in a single polymeric chain. How to do that? We can make use of the Boltzmann equations. The Boltzmann equations relate between molecular shape, the shape of the polymeric chains, and entropy of single chains. Okay, Boltzmann's equations. In order for us to use Boltzmann equations, you need first to describe how is the shape of the single chains. In which shape we can find the polymeric chain. So as you can see, this is relatively complex. we really need a lot of information regarding the molecular structure of the polymer. People have done this, okay, so it is easier for us to understand it because people have done it in the past. And then some of the things I will not go into much on the detail because of the complexity. I will just draw out some important result outcomes from each of the steps here. Some comment here. So various materials models for rubber can be derived using the previous steps. So these 6 steps are the guide for us. How we go to end with, to reach to destinations, to describe the stress as functions of strain. Various models have been developed, okay? Various equations have been developed. They difference in the descriptions of molecular shape or molecular conformation, which is step 1, and how they represent molecular network for the computations of entropy change in deformation step 4. So if I go back here, the difference is in descriptions number 1, and then how actually we count for the total change of entropy in the network from the change of entropy in each individual polymeric chain. So for the step 1, which deal with the descriptions of molecular conformation of single chain, 2 descriptions are typically used, Gaussian and non-Gaussian statistical theory. So I will not go into the detail. This is for your informations. While in the step 4, the network can be represented by a variety of ways. 3 chains, 4 chain, 8 chains, or full network. Okay, so one of the simplest concept model for rubber is the Neo-Hookean model, which is based on Gaussian statistical theory. Okay, so this is the models that I'm going to describe in the next slide. This is the simplest mathematical model to describe the stress-strain response of rubber materials. So, step 1 up to step 3 require basic knowledge of statistical mechanics. I will not go much into the detail of that aspect, okay? So to keep things easy, I will just briefly talk about steps number 4 to 6 so that you understand how we end up with the expressions of Neo-Hookean model. Okay. All right, so we go to number 4, basically. Change of entropy with deformations. So basic assumptions, again, I will not go much into the detail. So random walk, Gaussian statistical network, please look at in the literature, okay? So come up with these expressions, how the entropy of the polymeric chain will change with deformations. So delta SI, single chain, is minus KB square, and then you have terms here. Okay, and then here is that lambda. What I would like to draw your attention is this lambda 1, lambda 2, and lambda 3. These are the 3 principal stretches. So what does it mean? Let's say if 1 is directions along horizontal direction here, 2 is vertical direction here, and 3rd is along the thickness. Okay, lambda 1 is the deformed length over initial length. Lambda 2 is the deformed width over initial width. Lambda 3 is the deformed thickness over initial thickness. Okay, that's the meaning. This is the entropy, how the entropy change with deformation for one single polymeric chain. How about for the whole network, which consists of, let's say, n polymeric chains per unit volume? So you just simply sum up the contributions of each chain here and put it here. And then this is, after simplification, what you have. This is how the entropy change with deformations in the network, where n here is the number of chains, k is Boltzmann constants, and lambda 1, lambda 2, lambda 3 are the 3 principal stretches that I have mentioned before. So looking at the expressions of Helmholtz free energy, so delta psi equal to minus T delta S. So delta psi is psi minus initial psi, which we set to become 0 as a reference, initial energy equal to 0, minus T delta S. So if we insert the expressions of delta S here from the previous slide here, then we come up to the expressions of Helmholtz free energy for Neo-Hookean model, which is 1/2 times NKT, and then times the terms in the bracket here. Again, lambda 1, lambda 2, lambda 3 are the three principal stretches. N is the number of the chain in the polymer per unit of volume. K is a Boltzmann constant, and T is absolute temperature in Kelvin. Okay, so the terms NKT here is actually correspond to shear modulus. This is the shear modulus of rubber materials according to Neo-Hookean models. So the above free energy is known as a Neo-Hookean model. So few remark here. At constant temperature, the free energy depends only on deformations. If I go back here, at constant temperature means that if T is constant, K is a constant, N is a constant. So the free energy only depends on the three stretches here. So in this case, the free energy is also called as the strain energy density. So psi is equal to W. Okay, so in the next discussions, we focus on rubber deformation at constant temperature. Thus, the term free energy and strain energy will be used arbitrarily. So it will mean the same thing, okay? Either I say psi or W, it will refer to the same thing in the following. Okay, too much of the things, I guess. Before I stop in the example, do you have any questions? Let me know if you have a question so far. Are you following?
Yes, Doctor.
Okay. Does it sound clear? It is a complex process, but at least I would like you to understand the flow, how we end up, the logic, how we end up to get the expressions of W or psi or Neo-Hookean model. Okay? All right, now let's see. What should we do with whatever we have found in the previous slide here? Okay, what's next? Because our objective is to describe the stress-strain response. And then so far, we only obtain the expressions of free energy or strain energy. What should we do next? It is simple. If I can browse back here, which means that now I can compute number 5 and then later on easily get number 6. Okay, because now I already have the expressions for psi, and then I will need simply to differentiate with respect to deformations, and after that multiply by the length of the sample, then I get the expressions of the stress. As simple as that, the next stage. And that is what we are going to do in the first example here. Okay. So the question is that you need to derive the stress-strain equations, considered model or material models, these are the similar terms, for a rubber band under uniaxial tensile loading conditions. Assume rubber to be isotropic and incompressible. Use the Neo-Hookean strain energy density for this purpose. So isotropic means that the properties are independent of directions, and incompressible, we have discussed just now, it is the fact that rubber will deform at constant volume. Okay, this is the expressions of the strain energy. Now I change the term from free energy to strain energy, okay, which is half of G times this one, and then noting that the force per unit of volume is differentiations of W with respect to L. And this is the illustrations of uniaxial tensile loading conditions. Imagine that you have a rubber band. The initial length is L0. The initial width is W0. And then the initial thickness is T0. And then you stretch it along the length so that the length change to become L, the width change to become W, and the thickness change to become T. So the questions derive the stress strain equations. How to do that? Okay. Let me give you example because later I will give assignment relevant to this one. So I need you to make sure that you understand the process. Okay. If you do not follow, if you have any questions, you let me know. Right? Okay. So again, you already have the expressions for W or psi. You now need to differentiate it with respect to the deformations to get the force per unit of volume, and after that you get the force, and after that you get the stress expressions. Okay. So this is the basic equation. This is the Neo-Hookean equations. This is the force per unit of volume. First, we don't know yet which one is direction 1, which one direction 2, which one direction 3. So let's agree on the direction first. You are free to decide which directions you want to assign number 1, number 2, number 3. Okay? So again, you have 3 directions along the length, along the width, and along the thickness. So let me just choose that direction 1 is the directions of the length, direction 2 is directions of the width, and direction 3 is the directions of the material thickness. So that we have the stretches lambda 1, lambda 2, and lambda 3 as follow. So lambda 1 is L over L0. Lambda 2 is W over W0. And lambda 3 is T over T0. I hope this is clear. Yeah? You are free to assign which number to which directions. You can put L over L0 as lambda 2 or lambda 3. It's fine as long as you consistent with your choice. Okay? Note that L0, W0, and T0 are 3 constants. Why constant? Because it is the size, the geometry of your rubber band. It is only L, W, and T which will change with deformations. And then this understanding is important for you to do mathematical operations later on when you need to do differentiation. You need to clearly understand which one is the variable, which one is the constant. Okay, L0, W0, and T0 are constants. These are the geometry of your sample. L is the deformed length. W is the deformed width, and T is the deformed thickness. Their value will change information that we impose to the materials. Okay, I hope it is clear. So, if I use that notations, it means that because we conduct tensile tests along directions of the length, the stretching is imposed along direction 1. So we impose stretching along direction 1. So which means that lambda 1 is the given value. Because we stretch it. For instance, we want to stretch it 2 times, 3 times, or 4 times. We impose it. How much the amount of deformation that we want to introduce to the materials. And lambda 2 and lambda 3 will follow depending on the value of lambda 1. Because when you stretch it along direction the length, then the width will decrease, the thickness also will decrease according to the Poisson ratio concept that we have learned in lecture 4 before. Okay, which means that there is dependence of lambda 2 and lambda 3 on lambda 1. Okay, the more we impose deformation on directions 1, the more you have contractions along direction 2 and along direction 3, which means that you have now to link between lambda 1 and lambda 3 to, you need to link lambda 2 to lambda 1 and lambda 3 to lambda 1 also. I hope that is clear, yeah? I will repeat again one more time. I decided to choose direction 1 as the directions along the length. Because the stretching is imposed along the length, which means now it is the given informations. For instance, I deform it by lambda equal to 2, which means that I stretch it 2 times than its original length. Because the length increases, what I will have is that I will have contractions along the width, and I will have also contractions along the thickness. The width will decrease, the thickness will decrease. The more I stretch along the length, the more I have contractions along thickness and along the width, which means that lambda 2 and lambda 3 depend on lambda 1. So from these observations, I need to find the link between lambda 2 to lambda 1 and lambda 3 to lambda 1. Okay? Is that clear? Yeah? So how to link between lambda 2 to lambda 1 and lambda 3 to lambda 1? It is using the assumptions of isotropy and incompressibility. Why do we need to do this to link lambda 2 to lambda 1, lambda 3 to lambda 1? Because here, in order for us to proceed, we need to differentiate W with respect to L. And in these terms, only lambda 1 contain L. Lambda 2 and lambda 3 do not contain any L. But actually, there are link. Because lambda 2, lambda 3 depend on lambda 1. So we need now to express lambda 1 and lambda 2 as a functions of, we need to express lambda 2 and lambda 3 as a functions of lambda 1. So how to do that? First, we look at incompressibility and isotropy. Incompressibility means that the volume remains constant during deformations. So V equal to V0. Deformed volume equal to initial volume. Okay. And then what is the deformed volume? It is simply LWT. What is the initial volume? It is L0, W0, T0. So from this, you can make arrangements by using these expressions that lambda 1, lambda 2 times lambda 3 equal to 1. So when deformations occur at constant volume, the product of lambda 1, lambda 2, and lambda 2 and lambda 3 equal to 1. The product of the 3 principal stretches equal to 1. The second assumption is isotropy. Isotropy means that the materials will have the same Poisson ratio along direction 2 and along direction 3. They will deform in the same way, which means that lambda 2 will be equal to lambda 3. Which means that if I combine here with the first relation that I have from incompressibility assumptions, then I will have lambda 2 equal to lambda 3 equal to 1 over square root of lambda 1. Now, I managed to link lambda 2 and lambda 3 to lambda 1. So which means that I can now simplify the expressions for neo-Hookean hyperelastic strain energy from the original expression, which is this one, to become a simplified one in the case of uniaxial extension. Again, this is the simplified form only for uniaxial extension loading conditions. If you are dealing with other loading conditions, not uniaxial extension, for instance, you deal with torsions, you deal with bending, you deal with shear, then you will have different form of the simplified neo-Hookean strain energy. Okay, I hope this is clear. Okay, I'm trying to go slowly here. So the next is that once I have the simplified versions of the strain energy, I need to calculate the stress. Okay. When we deal with rubber materials, capable to undergo large strain, what happened is that if you consider cross sections, the cross section will change quite significantly with deformations because the material is capable to be stretched 3, 4, 5 times elastically. So which means that the cross section will decrease significantly, which means that if you calculate engineering stress and compare to true stress, the value will be significantly different. All right, so let's have a look to start with how we compute engineering stress. Or in later on, when we deal with rubber elasticity, it is called also as Euler-Kirchhoff stress, the first Euler-Kirchhoff stress. Okay, it is basically engineering stress, and then the second one is true stress. So what I'm going to do now is give you example for engineering stress, and then I will ask you to do for the true stress. Okay, so please pay attention for the engineering stress. Engineering stress is force over initial cross section. Okay, and then force equal to small f, force per volume, times initial volume over A0, so initial cross section. Can I put it here, the deformed volume? Yes, we can, because V equal to V0. It is incompressible. Okay. Now, what is the ratio between V0 to A0? It is L0. So it becomes F L0. So what is F? F is simply differentiations of W with respect to L times L0. And then we note that actually W is not a function of L directly, but it is a function of lambda 1. So we can make a simple chain rule here to differentiate. So differentiations of W with respect to L is simply W with respect to lambda 1 and differentiate lambda 1 with respect to L times this one. Okay, and then what is the differentiations of lambda 1 with respect to L? It is 1 over L0. So it will cancel out with L0 here. So we have only these terms. Okay, so again for this one, differentiation of lambda 1 with respect to L, I go back to the previous slide. This is lambda 1. Remember, L0 is a constant, L is the variable. So if I differentiate lambda 1 with respect to L, it becomes 1 over L. So in these expressions, this becomes 1 over L. So cancel out with, 1 over L0. It cancel out with L0 here. So you only end up with this one. So the engineering stress is differentiations of the strain energy with respect to lambda 1. Where is the strain energy? This is the strain energy that we have before. So when we differentiate, we have this one. So I will leave out few minutes for you to do for the true stress. Okay. Let's say 10 minutes break while you are doing for the true stress, for Cauchy stress. What is the difference true stress and engineering stress? The true stress is F over A, not A0. Okay, so please proceed with F over A and then see what is the final equation that you will get for true stress. I will stop for a few minutes, 10 minutes. Okay, I will be back at 12:28. Okay, for your informations, I have created link in the Spectrum for you to submit your answer. Okay, I open the submissions until 12:30. Please submit your answer to Spectrum. We will discuss it at 12:30. Okay, it's 11:32. So I saw some of you have submitted the response. So have a look for the. Let's have a look together now. It's the same things. It's very simple. Okay. The only difference is that we replace the initial cross sections with the current cross sections, which we can call as A. Yeah? So we do exactly the same thing. So F over A, again, F over V0 over A, or you can also replace it by V to make things easier. Okay, V over A, because V0 equal to V. And then V over A is simply the specimen length. So it becomes F times small f times L here. All right. So we do exactly the same thing. We have this times this. We do chain rule times this one. Again, the differentiations of lambda 1 with respect to L is 1 over L0. So L over L0 becomes lambda 1. So the only difference is that we have these terms, which is lambda 1. So this is the expressions of true stress, and this is the expressions for true strain. As you can see, the equations is non-linear. Okay, you have here G, which is shear modulus, lambda 1 minus 1 over lambda 1 square. It is highly non-linear equations. It is also sigma equal to G times lambda 1 square minus 1 over lambda 1. So you don't have the relationship G times lambda 1, G times lambda 1. It is not linear. It is highly nonlinear. You have this term here, which render the equations becoming highly nonlinear. Okay. So now if we go to the next example here, referring to example 1, plot the stress strain curve, both engineering and true stresses, by assuming that shear modulus is equal to 1 megapascal. Okay, so this one, again, to recall the expressions for the engineering stress, this is the expressions for the true stress. So we can plot it very easy. Okay, so this is the expressions for the engineering stress. So from lambda equal to 1 and then increasing, noting in mind that lambda equal to 1 correspond to non-deformed state. So there is no strain. So lambda equal to 1, L equal to L0. If we are dealing with the compressions, so lambda is less than 1, but more than 0. So lambda is always positive. It is the ratio of length of geometry. Okay. If lambda between 0 to 1, it means that we are under compressions. If lambda is more than 1, it means that we are under tensile. So this is the graph for the wide range, tensile here when lambda more than 1, and compressions when lambda is less than 1. So as you can see, this is the theoretical stress strain curve according to Neo-Hookean strain energy, where the value of shear modulus is assumed to be 1 megapascal. So this is the curve for engineering stress. Okay, it is non-linear. Apart from this one, where things gets more looks like linear, but in the beginning here, it is highly non-linear. How about true stress? It has different curve. Again, this is for the tensile conditions, and this is for compressions conditions. As you can see that whenever we are in the small strain regions, the true stress and engineering stress remains the same. But as the amount of strain increases, then we see the difference become much more significant. For instance here, if we look at, for example, for lambda equal to 3, true stress is approximately 8 point something. While here, if it is 3, then it is only about 3 megapascal, while here it is 8 megapascal. So you see that when we deal with rubber materials, now we need to be careful when we talk about stress, because we need to be very specific. As mechanical engineer, we need to be specific. We are dealing with materials capable to undergo large strain. When we said what stress is in the materials, then we have to clearly specify. Are you talking about engineering stress, or are you talking about true stress? In metals, when we deal with elasticity of metals, it doesn't matter whether you talk about true stress or engineering stress, because the strain is very small. The cross sections, the difference between initial cross section and deformed cross section is very small. So either you calculate engineering stress or true stress, the result will be the same. Okay, but in the case of rubber, where the material is capable to undergo large strain, the cross section may change significantly. That is why we need to be very clear when we talk about stress by specifying whether we are referring to engineering stress or true stress. I hope that is clear. Yeah. Any questions so far? Does it sound clear for everyone?
Okay.
Okay, yeah, Hadi, okay, yeah? All right. All right, so I have few slides to finish, okay, before we stop and then continue for the phenomenological approach next week. Some remarks on the things that we have discussed so far. So the neo-Hookean that we have developed before is based on Gaussian statistical theory, as I mentioned. And then it turns out that, okay, this is the observation, experimental observations, that the Gaussian statistical theory works well only for low to moderate change extension. Means that you can basically describe the stress strain characteristic up to, well, 2.5. Okay, so for higher chain extensions, okay, I see there are questions. I will go back to the questions, yeah, in the chat box. For higher chain extensions, the Gaussian statistical theory becomes inadequate. So if you deal with, for instance, applications where the rubber components are subjected to large amount of stretching, then you need something else. You need a better theory to describe the characteristic. So in this case, you need non-Gaussian statistical theory. And then there are a lot of models basically now developed using non-Gaussian statistical theory. For instance, if you Google it, find it in internet, you type 3-chains model, 8-chains model, 4-chains model, 4-network model, slip link model, and so on and so forth. These are various models developed by people to improve the capability of the model or mathematical equations to predict the stress strain characteristic of the materials. Okay, all right. Next, so this is the example of non-Gaussian, the mathematical models which is developed using non-Gaussian statistical theory. One of the most widely used, famous model, 8-chains models or Arruda-Boyce models. So Boyce, Professor Boyce is professor at MIT. Arruda was her students in MIT, who is now becoming professor also in Michigan. So they developed these mathematical equations to describe the stress strain behavior of rubber up to large amount of strain. So I do not show the derivations, just to give you the final result that this is the form of strain energy for Arruda-Boyce model. Okay, you still have here G, shear modulus. You have here N, which is the number of segment per chain. So this is a refined theory. So this theory requires us to look at one single chain, and the chain consists of smaller link, smaller segment, and the number of segment is represented by N here. Okay, and then there is a functions beta chain. Beta chain is given by these equations. L minus 1 of this. L minus 1 is the inverse of Langevin functions. You may never heard before. And then the Langevin functions is defined by this equation, hyperbolic cotangent. Okay, x minus 1 over x. So as you can see, and then lambda chain here is this one. it is much more complex mathematical equations. This is a physical approach. Okay, it tries to capture what we observe physically in the materials. And then you have another terms here, square root n, and then ln of beta chain over hyperbolic sine beta chain. So it's very complex, much more complex than Neo-Hookean. And then if we do a similar process to calculate engineering stress and true stress in the case of uniaxial extension, then this is the final expressions. Okay, engineering stress. You still have these terms similar like in Neo-Hookean, and then you have G, but in addition to that, you have all these additional mathematical terms. Similarly to true stress, you have this form, which is similar to Neo-Hookean. You have also G, but in addition to that, you have other terms there. Okay, so now let's compare between the predictive capability between Neo-Hookean models and Arruda-Boy's model. So again, Neo-Hookean models is based on Gaussian statistical theory, while Arruda-Boy's is based on non-Gaussian statistical theory. So here is the plot of engineering stress as a function of stretch lambda. Based on the theory, this is Neo-Hookean, on the solid line black here. This is using Arruda-Boy's. Okay, and then the circle here are obtained from experiment. So you compare the predictive capability of the mathematical equation to describe the stress strain response of materials. We now compare it with experiment. This is again if we use Neo-Hookean, where the value of shear modulus is 0.4 megapascal. So this is what we can get. As you can see that the result of the theoretical predictions coincide with experiments only up to almost lambda equal to 2. Okay, so only to when we strain it double, 2 times than its original length, the Neo-Hookean model is capable to predict it. But more than that, as you can see, you have quite discrepancy, and then even at much higher stretch, you have really large discrepancies between the predictions from the Neo-Hookean models and the real experiment. For Arruda-Boy's, okay, it consists of 2 parameters. Neo-Hookean consists only 1 parameters, which is shear modulus. For this one, it consists of 2 parameters, which is shear modulus and the number of segment. When we use this one, then we get the theoretical result, which fits perfectly with the experimental data. So as you can see that non-Gaussians improve significantly the predictive capability of the models. And this HN's model is an example of the mathematical equations to describe stress strain characteristic of rubber using non-Gaussian statistical theory. Okay, so as you can see, Arruda-Boy's perform much better than Neo-Hookean. Now, you are a mechanical engineer now. And then let's say that you need to give advice to your customer where the customer use elastomeric components for their parts. And then the customer asks you, they want to do finite elements to predict the stress strain behavior of the materials. Will you suggest the customer to use Neo-Hookean models or Arruda-Boy's models? What do you think? Which one would you suggest? Can you type in the chat box? Okay, naturally. Well, Matran, you said Arruda-Boy's. Okay, Arruda-Boy's. Hadi also Arruda-Boy's. Okay. All Arruda-Boy's. Anyone opt for Neo-Hookean? Arruda-Boy's. Looks like everyone's choose for Arruda-Boy's. So I agree with you that Aruda Boys is much better than Neo-Hokkien in the sense of the predictive capability. But as engineer, you need to understand the consequence of your choices. Okay? As you can see, Aruda Boys, it predict well the behavior, but the mathematical equation is very complex, which means that when you do the calculations, because it involves much complex mathematical expressions, the time needed to compute will be longer than Neo-Hokkien. That is the consequence. Okay, you may get accurate result, but the time needed to get the result will be longer than Neo-Hokkien because the mathematical equation is much more complex. So before you answer the question, you should ask first to your customer, well, what is the range of applications, the range of deformations that the materials will be used at? Okay. As highlighted, okay, Ibrahim, you have mentions there, very well. If the component itself will only be subjected to relatively small amount or moderate amount of strains, for instance, lambda equal to 2, well, there is no point to use Aruda Boys because even with Neo-Hokkien, we will be able to get much more or less similar result. So it will be better to suggest Neo-Hokkien in this case because it will give you not only accurate result but also faster result. Because when you do stress analysis for a complex structure, computer needs time to do the calculations with finite elements. The more complicated the equations, the longer the times needed to complete the calculations. However, if the applications impose that the components will be used at large strain, 5, 6, 7 lambda, amount of lambda, we don't have any choice. If we want to have an accurate result, then you need to opt for Aruda Boys. So again, this is, you need to make sure that you have a balance between your choice and the consequences. All right. If it is relatively small or moderate strain, maybe Neo-Hokkien will be sufficient. There is no need for you to use Aruda Boys. But if it is extremely large strain needed, then yes, Aruda Boys will be a good answer. Okay. So this is the last slide for today. Before that, I will go back to the questions asked in the chat box. Yeah, if you have any further questions, please let me know. For the usual case of elastomer, do we use true stress or engineering stress? Okay, again, this is depending first on few aspects. If you are dealing with relatively small deformations, then you may not have significant difference between true stress and engineering stress. That is the first thing. If you want to predict failure, because later on, the objective of conducting stress strain analysis is that we want to predict whether failure will occur or not, or if failure will occur, when it will occur. That is the questions. After how many number of cycle of loading that it will fail. In these situations, a lot of study have shown that it is better to use true stress. Yeah, when we want to assess the durability, we want to assess the strength of the materials, then it is better to use true stress. Yeah. For mathematical modeling, Hadi, I hope that answered your question. If you still have further questions, please let me know. Yeah. For mathematical modeling, how to decide which stress need to be considered true stress or engineering stress? Okay. First thing is, this is a good question. Something that you have to remember is that true stress and engineering stress can be related one to another easily. Okay. That is the first thing. So either you choose to express in terms of true stress or engineering stress, it is just a matter of which one that you prefer, because the two can be linked one to another. The next questions is that will be, because when we develop a mathematical equation or mathematical modeling, we need to compare with experiment. We need to compare with experiment, right? Like what we did just now in this slide, we compare with experimental data. Here, with experimental data, we may have more challenges. because the typical data that we have is in the form of engineering stress. So in that situations, we may need to adapt our choice to go to engineering stress. If we have sophisticated equipment so that we can measure experimentally the true stress, because why I said sophisticated equipment, because you need to have access to the size of the cross sections during the tensile test. Okay, so if we have enough sophisticated equipment to have the true stress data, then we can do the modeling on the basis of true stress. I hope that answered the question, Ibrahim. Okay, so it's for modeling, it's which one we use? Well, we know that theoretical true stress can be related to theoretical engineering stress easily. So it is just a matter of which one we prefer. But when it comes to validations, to check how good is our mathematical equations, we need to compare with experiments. And their experiments may have a challenge. It is much easier to get engineering stress data than to get true stress data experimentally. Yeah. Okay. Any other questions so far? Okay, great. Is there is there any relation between lambda and strain? It is a very good questions. Yeah, lambda is L over L0. The strain that you mentioned, I presume you are referring to engineering strain, correct? So yes, there is. Let me just write here directly in my slide, just to make things easy, because I will just please apologize for the format. Okay, I can write in red. So lambda, just for lambda, is equal to L over L0. Okay, and then we know that strain is equal to dl over L0. Is there any link between the two? Yes. If you come back here, okay, L is, this is equal to L0 plus delta L, and this is over L0. Okay, and what happened is that it is equal to 1 plus dl over L0. Sorry, this is dl, and then this one equal to 1 plus strain. So lambda is equal to 1 plus strain. I hope that answer your questions, yeah, Matran. So lambda, which is stretch, is equal to 1 plus strain. Okay. Is there any other questions? Okay, so I hope I understand that some of the theory I leave out. I do not go much into detail because of the complexity. Okay, but I hope that you manage to capture the idea, the flow, the logic on how we can develop mathematical equations to describe the stress strain characteristic of rubber. Okay, and then we have seen using the physical approach, when we really look at the structure of the materials, we look at the conformations, the shape. From the shape, then we use Boltzmann's equations, relate between the conformations to the entropy, and then from that we evaluate how the entropy of one single polymeric change will change with deformations, and then how we sum up the contributions of individual chains to the whole network to get the value of the change of entropy of network with deformations. And then from that, we get the expressions of free energy or strain energy. From the strain energy, then we can directly compute the value of engineering stress and true stress. So this is the step, the flow, that how people do to develop mathematical equations. I have shown you the simple case of Neo-Hookean, which was developed using Gaussian statistical theory. It works well up to moderate strain, but for larger strain, you need more sophisticated theory, and this is provided by non-Gaussian statistical theory. All right. So we have seen both, and then next week we are going to discuss about using the phenomenological approach, where there is no need for us to look at the microstructure. So we need some basic knowledge of continuum mechanics. So I will briefly introduce very quickly basic notions of continuum mechanics for us to describe the stress strain behavior. Okay, if there is no further questions, I will see you next week. For those who celebrate Christmas, Merry Christmas. And then happy long weekend to the rest. And then I will see you next week for the class. Okay? All right. Thank you very much. See you next week.
Thank you, Doctor.
Thank you, Doctor.